Good morning, everyone. It is a great pleasure to welcome you all to the Global Water Futures Core Modeling webinar series. My name is Praveen Rokhaya. I'm the science coordinator of the Core Modeling and Forecasting team. And I want to thank you all for joining us today, despite many online meetings and webinars we have these days. So we really appreciate your engagement. Today we have Professor Martin Clark from the University of Saskatchewan, who will be presenting on the advances in geospatial intelligence. It would be about 45 minutes of presentation, followed by 15 minutes of question and answer session. Before we begin, I want to share that next month on 4th of February, we'll be having Professor Roy Brouwer from the University of Waterloo, who will be presenting on advances in hydroeconomics, so please stay tuned. Today, I'm very pleased to introduce Professor Martin Clark. Martin is one of the co-leads of the Core Modeling and Forecasting team, and also the faculty lead for the Geospatial Intelligence team. This team focuses on developing advanced capabilities on model configuration, process-based parameter estimation, and model evaluation benchmarking, which I believe Martin will be highlighting today. Martin, we are very happy and grateful to have you here today. The floor is yours.
Okay, thanks, Praveen. Let's just get started. Well, as Praveen mentioned, what I want to talk about today is some of our work on model configurations, talking about model workflows, some of the work on parameter estimation, and some of the work on model evaluation, and then we'll sum up at the end. So if we get started, what we're interested in hydrological modeling is to provide a meaningful spatial representation of the landscape. So what we do in a lot of models, and this is an example from the SUMMA model that I'm most familiar with, is that we've got a hierarchical spatial structure where we have hydrological response units that are nested within grouped response units. And the hydrological response units and grouped response units can be any size and shape. So a grouped response unit could be a grid in a traditional land model, it could be a subbasin in a catchment, and the hydrological response units could be hydrologically similar areas within a subbasin, different vegetation types within a land model grid box, etc. So with that general spatial organization, it becomes possible to mimic the behavior of a lot of existing models. The columns that we have define the HRUs, and they can have different configurations representing just the vadose zone, or the vadose zone connected with an aquifer, or multiple soil columns feeding an aquifer for the entire GOU, or multiple soil columns that are hydrologically connected. We use this to provide input of water to the river network, and then based on that, we're able to simulate hydrological processes, across large domains. This is just an example over North America. And of course, to get to these types of simulations, there's a lot of science questions that we need to answer. And a lot of the questions are associated with how we could be more effective and efficient in the way that we configure our hydrological models. We often see hydrology as being a square peg round hole type problem. So often, we see many in the community as being relentlessly rectangular, and still a lot of approaches to drape a grid over the landscape and expect to solve a lot of the grand challenges in hydrology. So we've seen that what we're talking about here is more of a vector-based representation of nature to represent the features that are really important in nature, so that we can get closer to the hydrological processes that are important. The challenges that we have is that modeling the terrestrial water cycle depends on the unknown details of the landscape. Increases in horizontal resolution often don't lead to increases in model performance. That's quite different than what we see in the atmospheric sciences, where you can magically begin to resolve more and more processes as you go to a finer resolution. And because of this, we need some creativity in how we discretize the model domain in space. So the key challenge that we have in hydrology is on spatial scaling. So we're interested in developing flux parameterizations that represent the aggregate impact of subgrid scale heterogeneities. So there's different ways that this has been done in the community. One approach is to explicitly represent spatial variability. So that can be done with a high resolution spatial mesh. separate computations for process subsets. So we may have separate computations for snow-covered and snow-free ground, separate computations for the shaded area of the canopy and the sunlit area of the canopy. We may have representative hill slopes to define subsurface flow processes at the scales that are important. We may use hydrological similarity metrics to lump similar areas of the landscape together. But then we also have different methods to estimate the element average fluxes to implicitly represent the spatial variability. So we know that many of our parameter values estimated at a point may not be appropriate at larger spatial scales, so they may need to be upscaled. We may need new flux parameterizations or smoother flux parameterizations at the spatial scale where the model is applied. Or we may want to capture, the unresolved spatial variability using subgrid probability distributions. There's many methods for doing that that have been published throughout the literature. So what we're getting to now is to think, okay, all models have got similar data requirements. So how could we be more effective and efficient in the way that we configure our models? So a lot of what we're doing is based on global data sets. So we want to be very general. This is an example of the Merit Hydro database, which has discretized a large number of sub-basins around the world. This is available globally, and here I'm showing the Saskatchewan River Basin and zooming in to the Bow River. So what I've highlighted here is the Bow River above Calgary, which you can see there. That's Calgary here, east of the Canadian Rocky Mountains, and then zooming in even further for the Bow River at Banff. And in Canadian hydrology, a lot of people talk about where models go to die. The Bow River at Banff really is the place where modelers go to brag, because the modeling problem can be viewed as, a lot easier than many other parts of Canada. Now, show some reasons for this a little bit in reference to some of the work that Wouter Knerven has been doing. So we have the land model providing the information, and we have runoff at the HOU level. And then we can have hill slope routing to route that to the HOU outlets, river reach routing to shunt water through the river networks and to provide stream flow, at every point in the river network. So what we've been doing, we've been spending a lot of time on the Merit Hydro database, stitching in the coastal catchments and developing topologically based numbering systems to enable and simplify a lot of the modeling that we're doing. And also, incorporated lakes and doing the geospatial work to link to lakes. And this is forming the basis of the computational infrastructure that we're using for a lot of our large domain hydrological models. This is primarily work that's been done by Shurvan Gahari in collaboration with my colleague Naoki Mizukami at NCAR. What we're seeing here is just an animation of flow in the Mackenzie River Basin, showing the coupling of simulations of stream flow for the river network and also, the major lakes. If we look at Great Bear Lake, in this example, we're in the right ballpark, but this is really just the base computational infrastructure that's been set up, and we've got a lot of work to address the science questions associated with hydrological modelling in these basins. A lot of other work in similar veins. Chris Marsh has been working for many, many years on developing the Canadian hydrology model. And this is an example here where he's using an unstructured mesh to have variable resolution representations of the landscape. This is an example here of a mesh that is generated with topographic and vegetation constraints. He can move this forward and say, okay, if we've got different error metrics and the way that we use in the mesh generation, we can have like different meshes of different resolution that provide different representations of the topography at different levels of fidelity. So he's got the flexibility there and a big tool set associated with Mesher developing to enable those capabilities. The triangular representation is great for a lot of modeling applications. It's perhaps limited, for some other modeling applications, and there's a lot of other things that go into this as well. So in order to get the CAtchment working, we need the percent tree cover, the digital terrain model, the water mask, some LiDAR information, global canopy height, etc. And when we're mapping on, what Chris is doing, and what people are doing in mesh, and people are doing in the cold regions hydrological model that John Pomeroy has been leading over the past 20 years, many of the data requirements are really quite similar. So this is motivating a lot of shift to flexible-based spatial configurations and land models. This is work that Shiv Angari published a couple of years ago, looking at spatial configurations at different levels of complexity, going from 1 to 4, and spatial configurations at different resolutions, going from 4 kilometers to 2 degrees. And what this figure here is just showing the difference in the Nash-Sutcliffe score. And the key result from this figure is that when you're looking at the main stem, this is for the Bow River at Banff again, that the difference in the Nash-Sutcliffe score doesn't change much as we're aggregating to larger spatial scales, as we'd expect. The main benefit of this paper is that it's providing a generalized framework to advance how we can get better representations of the landscape and the modeling that we're doing. This is all kind of leading forward to the work that Wouter Knerben has been leading on model agnostic model instantiations. So as I mentioned in a couple of slides ago, I said that while most models have got similar data requirements, they're often configured in an individualistic and ad hoc way. And that makes it more difficult to reproduce results and share workflows across different modeling groups. So what we're doing with Wouter is really pushing forward and trying to say, well, okay, to what extent can we have model agnostic workflows so that we can improve the effectiveness and efficiency of the work that's going across multiple modeling groups. So I've got some examples here. So this is an example of the Merit Hydro database, where there's about 0.6 million catchments in North America. It's about 2.7 million catchments worldwide, or about 3 million catchments worldwide if you count all of the coastal catchments. And when we're working on setting up models, we've got data requirements associated with how we deal with the topography, how we deal with soil, vegetation, forcing data, the river network, etc. So skip through this and the subsequent slides. So when we're dealing with topography, we may need to download the shape files, delineate the coastal hill slopes, convert to an equal area projection, calculate catchment area, and then provide the information when we're doing the SUMMA runs, for example, in their attributes file. We've got some additional tasks where we need to download the DEM data, intersect the basin shapes in the DEM to calculate the mean basin elevation and the other topographic attributes that we need. And again, insert those into the attributes.nc file. We're interested in soil data, so we download the soil grids data, convert it into sand, silt, clay percentages, find the mode soil class across depth, intersect it with basin shapes and soil data, find the mode soil class in each basin, and insert that information into this SUMMA attributes.nc file. Similar for MODIS, we need to download it, do some processing of the files, find the modes, do the intersection, etc., and then put that into the file. And we go through, we're interested in forcing with error 5 as an example, so we need to download that data, do the processing on it, combine wind vectors, and do the intersection, compute basin average forcing, and then create the SUMMA forcing files. And then for Merit Hydro, interested in downloading the network data, matching the network to the model domain, create the MISRAP files, etc. So when we pull all of this together, we're interested in basin delineation, digital elevation data, soils data, vegetation data, meteorological data. we can see that there's just a few tasks at the end that are model specific. Most of the tasks that we mentioned here are tasks that are required in some form or fashion for most hydrological models. So what we're interested in is simplifying this, or what Wouter has effectively completed is simplified this and said, okay, we've got tasks for domain specification, processing the parameter data, processing the forcing data, processing the routing data. Most of those tasks are model agnostic, and then we've just got a few tasks that are model specific. So the goal there is to separate both of those to develop the model agnostic workflows. So what we have and what we're beginning to work with other modeling groups is a thin interface layer between the model agnostic pre-processing and the model specific files. So this is all pushing forward to improve the efficiency of continental domain model implementation tasks. As I mentioned before, it's to make it easier to collaborate, easier to keep track of the work for reporting and paper reviews, increase transparency, reproducibility, and code reuse. But what we're really trying to do here is advance community hydrological modeling rather than a community hydrological model. We recognize that different models have different purposes and different communities. And it's difficult for us to converge on, a single model that will be the ring to rule them all, so to speak. But what we can do is recognize that many of the modeling groups have similar tasks, and if we think as to how we can encapsulate those tasks and provide a model agnostic framework, then we can do a much better job of developing a community of best practices for both the science and applications community. There's some work that's just started really on taking what Wouter's done and looking at the applicability in mesh. So this is work that Ala Barami is leading. So on the left, we've got SUMMA in terms of what I just showed, in terms of the data acquisition and pre-processing, domain specification, looking at the forcing data, the parameter data, the routing data. Similar tasks that we have on the right for mesh. The big stumbling block in mesh really is the square peg round hole problem and the backflips that are necessary to make hydrology work on a grid. So that's being looked at in a little bit more detail. And then also in mesh, talking with Dan Prince and others, there's some constraints in that the work that's done for the soils data and the vegetation data is not necessarily as automated and as agnostic as it could be. In mesh also, there's the work for mesh routing to avoid the square peg round hole problem and advance mesh to a vector-based routing method. So there we're taking the configuration that we've developed for Mesoroute and all of the data that we've developed for Mesoroute and trying to incorporate that in the mesh framework. Again, this task is, just starting up, but a lot of early progress has been made on this. I'm looking forward to see what's possible with this, as we're moving forward. I'm hoping that both of these tasks will really accelerate the mesh instantiations for some of the major basins across Canada. One of the things that Shirvan Gahari has been doing again to support a lot of this is developing the CANDEX. This is the CAtchment NetcOf Extractor for remapping forcing or model output variables. So this is effectively providing the capabilities to map information from any polygon, and a polygon can be rectangular, to any other polygon to accelerate a lot of the spatial remapping tasks that we have in hydrological modeling. What I'm showing in the figures here is the Saskatchewan River at Medicine Hat, and an example of taking temperature from Era 5 and remapping that to the subbasins that are used in the hydrological modeling. The workflows are also being used in forecasting. So this is work by Louise Arnall, where a lot of tasks to develop the CONUS-wide inputs, hydrological modeling, forecast generation, forecast verification, predictability and analysis, etc. A separate set of workflows or a superset of workflows. And when we're getting into the forecasting work, this is work that Louise has been doing in collaboration with Andy Wood. And then now Louise is beginning to work closely with Chris Marsh to see how a lot of these workflows using EasyFlow and other workflow management systems map onto the work that's been done in Snowcast, and beginning to unify some of those capabilities. Here's an example here. This is some work that Louise has been doing to activate these workflows and provide some initial instantiation. So this is the work that she's been doing for the Kootenay River at Fort Steele, and some example ensemble streamflow forecasts that she's been developing using those workflows. Okay, so if we pivot to the parameter estimation, there's a couple of aspects here. We're interested in the sensitivity analysis to understand the model behavior and large domain parameter estimation. But first, some parameter definitions. So in models, we often think about a hierarchical topology. We've got the architecture, which is the selection and arrangement of the state variables. We've got model parameterizations, which are functions that we use to describe the relationship between the model states and the model fluxes in general. That's kind of a starting point for hydrology, and there's some specific differences, when we get to other parts of the terrestrial system, and model parameters, which are typically the adjustable coefficients in the model equations. When we look at this in complex models, the parameters are distributed throughout the code in different points in the model workflow. So there can be parameters associated with transfer functions, like payload transfer functions that are used, for example, to relate sand, silt, clay content to hydraulic conductivity. Lookup tables, vegetation properties for different plant functional types. Hard-coded parameters. There's a problem in some models where parameters are hard-coded and effectively represented as physical constants, and then some nameless parameters that may be spatially constant. So when we're dealing with complex models, we've got to understand where all of the parameters are and begin to unify that in a meaningful way so that we can characterize the uncertainty that's there and use the data that we have to refine our estimates of the model parameters. There's different methods for sensitivity analysis. The most common or simple is one-at-a-time analysis. So that's where you may perturb one parameter while keeping all other parameters constant. More sophisticated approaches for local sensitivity analysis, where we can perturb the parameters, at one point in the parameter space, calculate different metrics, etc. And then global sensitivity analysis. So global sensitivity analysis is that we're not just interested in one point in the parameter space, but we perturb parameters throughout, a wider parameter range. Some examples of global sensitivity analysis are Sobol, variance decomposition methods, etc. Often the reason for sensitivity analysis is to understand how the model behaves, or to identify a subset of parameters that you may want to use in model calibration. What we're interested in core modeling is to understand model behavior across large domains. What I'm showing here is a paper by Steve Markstrom that was published in HES, a few years ago. I was involved in this paper, and this is looking at parameter sensitivity analysis across the contiguous United States. What I'm showing in the figure there is the number of parameters that explain 90% of the variance for different fluxes and state variable, for different fluxes that are important across the contiguous United States. So the work at PKIC is really beginning to push this forward in Canada now. It's really nice to see. This is work by Samar Larabi, who's working with Marcus Schnorvis at PKIC. So they're interested in identifying calibration set parameters prior to calibration based on how parameters affect different model outputs. So they're doing the sensitivity analysis for a large number of basins, large number of sub-basins, in the Fraser River Basin. So some of the driving questions are how sensitive parameters change across a large domain with the dominant physical and climate characteristics. How enough sensitivity information can be extrapolated instead of running large-scale sensitivity analysis. So can they do the sensitivity analysis for the subset of the domain and provide information that's useful for the entire domain? And how do the dominant model parameters change depending on the model output of interest? So it links back to the Markstrom paper that I showed on the previous slide. So they've been making good progress here. What they're using is the parameter screening method that's proposed by Matthias Kuntz at 2015. Julie Meyer was a co-author on that paper. So what they're doing here, it's effective, the method of Morris and the elementary effects, where they're looking at parameter perturbations in different parts of the parameter space. But what they do, if a parameter is already sensitive in one part of the parameter space, then they say, well, we know that parameter is important, so we're going to remove it from the analysis and focus on the parameters that have not yet been deemed important. So they're already beginning to identify different categories of parameters that are identified, the parameters that are informative for all basins, some non-informative parameters, and parameters that have no sensitivity agreement among basins, where they can be sensitive in some basins and not too sensitive in others. In our work, we've been developing a new computationally frugal method. The problem is that a lot of the existing computational frugal methods, like the elementary effects method that is currently being used, doesn't, and DELSA, like the distributed evaluation of local sensitivity analysis, other methods like that, don't provide the same information that's obtained through various decomposition methods. So our solution is to use copulars and Gaussian mixture models to estimate the parameter response surface and calculate the formal sensitivity metrics. So this is a paper that we've got under review in Water Resources Research at the moment. And what we're seeing, we applied it to the VIC model and the HPV model for the Bow River at Banff, and finding that, well, the parameters have got different names, but the groups of parameters that are strongly influential, moderately influential, and least influential, are similar across models. It's pretty early days with this method, but I'm pretty excited about it because I think that this method can smooth out, a lot of the numerical errors that can contaminate some of these variance-based sensitivity analysis metrics, as we showed in our 2010 paper on numerical methods in hydrology. So with the smoothing, thinking, still hypothesis at this stage, that this method has got a lot of applicability to provide robust estimates of parameter sensitivity across large geographical domains. When we're interested in parameter estimation, it's really learning from data. A lot of people think about parameter estimation or model calibration with the models as mathematical marionettes that dance to match the calibration data, even if their premises are incorrect, where we spend a lot of our time to get the right answers for the wrong reasons. But what we should be doing is thinking about parameter estimation from a process perspective and how we can use the data that we have to inform our understanding of the parameters in our model and how the parameters describe processes that are important, such as the transmission and storage of water across the landscape. For large domain parameter estimation, we often need some spatial regularization method. So we've got the parameters that are a function of some variable given some other parameters. So X here could be a priori parameters, or it could be geophysical attributes, and gamma here is the coefficients in a transfer function. So the simple case is a parameter multiplier where we're interested in the ith parameter, and here what we're doing is estimating the parameter multiplier that relates an a priori spatial estimate of that parameter to the parameter that's important in our model. Gamma can also be a coefficient in a transfer function that's used to relate geophysical attributes to model parameters. Some of the earlier work that we did across the contiguous United States, a lot of the work and the water security assessments was based on basin by basin parameter estimation methods, leading to spatial discontinuities in the model simulations. A lot of the spatial scaling work that's been done by Luis Samaniego begins to address this. So we're saying, okay, let's start from the beginning, and this is getting back to the workflow things that I mentioned earlier, where we've got soils data from soil polygons. We may estimate model parameters at the spatial scale of the soil polygons, and then do some vertical upscaling and some horizontal upscaling that we need in order to do our model simulations. When we look at that and contrast that with the traditional approach, the traditional approach is that we may have a preprocessor that's regridding the parameters to the spatial elements that we use in our model. Then our model has transfer functions to estimate the model parameters based on geophysical attributes, and then adjust those parameters using parameter multipliers or something like that. What Luis does in effect is includes the preprocessor as part of the model calibration. So he goes all the way back to the transfer functions that are used to estimate model parameters based on geophysical attributes, and adjusts the parameters in the transfer functions with appropriate upscaling operators to provide model simulations. By design, when we apply this, we naturally remove the spatial discontinuities that we had in both the parameters and the simulations of runoff. When we bring all of this together, what we have is like three legs of a stool, so to speak, or three vertices of a triangle, where we have geophysical attributes that we're interested in relating to hydrological signatures, evaluating the information and attributes that relates to signatures, using the attributes and regionalization approaches to estimate the model parameters, and then understanding how perturbations in the parameters can affect the hydrological signatures through some type of sensitivity analysis. This is all statistical in nature, and the process linkages are missing. So there's a need to study the process interactions across timescale, move away from the traditional paradigm of properties defining processes, and understanding how processes define properties to provide some hydrological theory behind a lot of the parameter estimation work that we're doing. As an example, how does landscape evolution define the storage and transmission properties of the landscape? Okay, so model evaluation. I want to start by talking about the use and abuse of traditional performance metrics. The classical approach to model evaluation is that you've got a system and a measurement of the system on one hand. On the other hand, you've got a model, and models providing simulations, and you're comparing the two based on some measure of closeness. What we did recently was we said, well, okay, how uncertain are those methods of closeness? So we looked at the Nash-Sutcliffe uncertainty for 671 basins across the contiguous United States, and found that the Nash-Sutcliffe estimate of uncertainty, was typically between 0.1 and 0.2, for many basins across the contiguous United States. Huge uncertainty there. And that's really, really important, because often, what we see in the modeling community is that people are getting excited if they move from a Nash-Sutcliffe score from 0.78 to 0.81 or something like that. And we can see that that's really in the noise level. We can look at the uncertainty in the uncertainty. So we've got some methods that I don't have time to get into here, and that's saying that even though the uncertainty is large, and that we've got some uncertainty in the uncertainty, that the problem is still pretty significant, and that when we're looking at traditional metrics for model performance, we need to do a much better job as to how we characterize the uncertainty in those metrics, so that we're not contaminating the conclusions that we draw from some of those studies. But for model evaluation, we're not really interested in a single metric of model performance. That's nice as summary metrics that, we often have to include in our papers to provide the summary statistics of our study. What we see is that there's a data dimension that's typically compressed to 1. a parameter dimension that's typically compressed to 1, and we're using a single model metric to evaluate the fidelity of our model simulations. Where we need to go with this is some artwork from Louise Arnal, is really pivot a much greater degree from the paradigm of accuracy to fidelity. So accuracy is what we typically see that describes discrepancies between model simulations and observations. And fidelity really describes the extent to which a model faithfully represents the dominant processes in the region where it's applied. So what we're doing in this project is opening up the black box, so to speak, and really understanding how the model behaves and having a much more comprehensive evaluation of the model fidelity. One of the things that we've done as a precursor has been looking at laugh tests for land models, or synthetic test cases, or functional unit tests. So this is kind of a nice thing to do. We're viewing this as an entrance examination for land modeling in to some extent, asking the question, like, have we implemented the model equations correctly? What are the impacts of the numerical approximations? And these laugh tests are really providing the most rudimentary test of model capabilities. If a model fails a laugh test, then it's really difficult to seriously consider the use of the model for its intended applications. So here's an example. This is an example of infiltration into dry soil, and this is a classic example, that's being used in Vadasone hydrology. It's introduced by Mike Seeley et al. In his classic Richards equation paper. So we've got simulations of volumetric liquid water content with depth, at different times. And our colleagues, Ray Spiteri and Kevin Green in the computer science department have been looking at how some of their adaptive spatial mesh approaches can be used to solve some of these problems. So that's the figure there that I'm showing on the left. Another laugh test is steady state flux in a layered soil profile. So this is from Vanderburgt. This is a nice test because we've actually got an analytical solution. So we can look at the vertical profile of matrix head and evaluate the extent to which that compares against an analytical solution. We can have laugh tests for water movement through snow. So this is originally coming from Colbeck 1976, where he had rain for 3 hours on top of a 1 meter snowpack. He didn't complete that solution. We completed the solution a few years ago and figured out how to provide an analytical solution for volumetric liquid water content in the snowpack at every point in space and time. So we can check under his 3 scenarios, initializing with ripe snow, refrozen snow, fresh snow, that our model simulations match the analytical solution. We also have simulations of outflow from the bottom of the snowpack, and again able to check that our numerical simulations match the analytical solution. In our numerical solutions, we do have some numerical diffusion that we don't actually see in the analytical, that's not present in the analytical solution. But we don't view that as a limitation of the numerical method. That's really what we expect. Another laugh test is cryosuction, where we're getting migration of water to the freezing front. So this was a lab column experiment where columns of soil were subject to cooling from above, starting with uniform liquid water content, and here we're evaluating the extent to which our model simulations reflect, the generalities of the process and compare to the laboratory observations, for this case. So to sum up our laugh tests, we've really got 3 different tests. One's to compare to simulations from other papers, another's to compare to analytical solutions, and the third's to compare to lab experiments. They're considered the most rudimentary test of model capabilities. and are really used to evaluate the implementation of the model equations, including the impacts of the numerical approximations. So we think that they're useful not only as an initial sanity check that everything's implemented correctly, but also as a major check that's used in continuous integration to make sure that when we're making new changes that we're not corrupting the most basic modeling capabilities. We're also interested in process-based model evaluation. This is now getting a resurgence with Al Petronero, who's beginning to jump into this with a considerable level of gusto. So we're interested in continental-wide process-based model evaluation, research basins, and point basins. We're interested in different processes and using data that's dependent on both the process and the scale. So at continental domains, we can use satellite observations of snow cover. And as we're getting into the research catchments, there's a lot of snow course observations and flux tower observations that we're able to use. Different types of process signatures that we can use. And this is MODIS, on the continental domain. This here is a paper by Drew Slater, who's published a few years ago, and he was saying, well, actually, one of the key signatures that we can use is the relationship among variables to evaluate the overall behavior of models. So what he did is he took data from a number of locations with observed air and 20 centimetre soil temperature plus snow depth, and was able to look at the general relationship between effective mean snow depth and the normalized temperature amplitude as a way of evaluating frozen soil parameterizations. So the grey shaded area in this figure is what he's getting from observations, and on top of that he's looking at the behavior from multiple models and using this as a diagnosis of model behavior. Some others, we've got like large samples of catchment now over the US. We're extending this into Canada and having multiple models applied to all of those catchments, and so that we can evaluate not only how the models behave, but how the models behave compared to benchmarks describing well-published models in the past. So enabling us to ask the question if we're improving on current modeling capabilities, or if we're not improving on current modeling capabilities, able to dig in and begin to evaluate why. Model benchmarks. So benchmarks provide context for model simulations, and they're widely used. The traditional benchmark is a skill score, which is 1 minus some error metric divided by some reference. So if we consider the mean squared error, which is an error metric, and a reference error metric, you can calculate that skill score. The reference error metric in this case is just the variance of the observations. And as many people would already know, if we calculate this as a skill score, 1 minus the mean squared error divided by the variance of observations, that's exactly the same as the Nash-Sutcliffe efficiency. So here the variance of the observations is being used as a benchmark to provide context for the model skill that's being calculated. There's been some criticism of that in terms of, well, what's an appropriate benchmark? Should we really be trying to evaluate the variance of the observations? So there's this famous paper by Bettina Shafley and Hoshin Gupta in 2007, a long time ago, that's saying, well, that benchmark's really easy to beat, especially where there's strong seasonality in the flow regime. And can we have better benchmarks, like simulate departures from the seasonal cycle? So another benchmark can be based on theory. So a question is, can we predict departures from the Bodico curve? So the Bodico curve is a really simple model that describes the partitioning of precipitation into evapotranspiration and runoff. We've got different observations of that partitioning and different models. So do our models provide more information than that simple benchmark? We would expect them to do so because, like, data issues notwithstanding, because our models have all of the processes in them that describe departures from the Bodico curve, like precipitation intermittency and things like that. What we see is that most models, this is for the plumber experiment, do not beat the Bodico curve, suggesting that they're not adequately using all of the information that's available to them. This is work from Wouter Knurbin, building on some of the work from Bettina Schäfli and Hoshin Gupta. And they're saying, okay, let's use the mean seasonal cycle as a benchmark and evaluate that across a large geographical domain. So this is what they did, and they found that looking at the Kling-Gupta efficiency using the seasonal cycle as the benchmark is that getting really, really high values of the Kling-Gupta efficiency in the snowmelt dominated river basins, saying that KGE scores are really, really high where there's a strong seasonal cycle. And then if you're looking at the model KGE versus, the benchmark KGE, while we see spatial plots with the KGE being quite high for the model simulation, when we use the seasonal cycle as a benchmark, the improvements aren't really that dramatic. We could also use upper benchmarks to define the predictability of the system. So that's asking the question, to what extent does the model use the available information? So here's an example with the VIC model, where we're using a really simple calibrated conceptual model as the benchmark. That's in the black there. So this is the benchmark that's used by the river forecast system. And so here we're saying, can a calibrated conceptual model be used to extract information out of the input response data to provide an estimate of the maximum information content in the system? And then we're asking the extent to which process-based models can match that upper limit of predictability. Jan Siebert has been working on this as well. He's been talking about upper and lower benchmarks in hydrological modeling. His upper benchmark is what we used and that predictability assessment, the best possible performance with a calibrated model. And then his lower benchmark is saying, well, okay, how well can we do with a random parameter set within feasible ranges? Or how well can we do with a calibrated parameter set for a nearby catchment? But again, it's the same philosophy as to how can we use different metrics to provide context for the model simulations that we're interested in. Okay, so if we sum up, I want to talk about each of these themes that we've been pushing. Model workflows, most of the work that's been led by Wouter Knurbin. Our goal here is to improve the efficiency of continental domain model implementation tasks in order to make it easier to collaborate, easier to keep track of the work that we've done, easier to deal with paper reviews, and increase transparency, reproducibility, and code reuse. As I mentioned, it's model agnostic. We're beginning to look at the application of these approaches for the mesh model, and then we've also had some discussions with Chris Marsh to begin to think about how some of this work can be used or combined with the work that he's done for CAtchment. And again, we're really interested in pushing the paradigm of community hydrological modeling rather than a community hydrological model. Further parameter estimation work, this is really beginning to get off the ground now, so that's pretty exciting to see. The sensitivity analysis, so the work that the PKIC group has been doing and understanding spatial variability and model sensitivity across large domains, the examples that I showed for the Fraser from Samal Arabi. Some of the work that we're doing for new sensitivity analysis methods for large domain hydrological model simulations. We think that work will have some applicability as we're moving forward. But still a lot of work to do there to understand model behavior across large domains. Work on large domain parameter estimation is going to get started soon. So I mentioned the need for regularization. The main stumbling block that we have at the moment in Canada is that there's many methods available for large domain parameter estimation, and we don't really have a good understanding of the advantages and limitations of those different methods. So that will be a key focus for us as we move forward. But then with the parameter estimation, one of the key hallmarks of the Global Water Futures program is to be able to connect the field insights with the modeling. So we need to step back and understand everything that we're doing there and circle back to understand how parameters link to processes, so that we're not just doing these statistical backflips where our models are mathematical marionettes. For model evaluation, that's been going well. We've got the LAF test paper, which I talked about, synthetic test cases of functional unit tests. That's halfway through the review process. We have to revise it and send it back in, and we hope to do that this week actually. A lot of recent effort on the process-based model evaluation, with Al really focusing on the research catchments to start with. So I'm really looking forward to see how that will progress over the next few months. And with the model benchmarking to do a much better job to provide context for our model simulations. So that's all I have actually. So I'll pause there and see if there's any questions. Thanks a lot.
Thank you, Martin. That was a very informative presentation. We'll be now moving towards our question and answer session. So I'll just let the questions pour in, and I'll just ask one small question that I have is, so I believe the geospatial intelligence, it can provide much of the underlying fabric to other themes. So the activities that are undergoing our plan are very fantastic. But can you talk a little bit on the timeline and how and when there will be this transfer of knowledge and tools to other themes?
Well, yeah, that's already happening. So one of the key linkages that we have is with current generation hydrological modelling. So the theme that Bruce Davison is leading on configuring mesh, for the larger basins across Canada. That's been difficult, as I understand. I don't want to talk too much for Bruce, because there's some pain points in the model configuration. So our work with the mesh group has focused on two areas. The first is on the vector-based routing, because one of the major pain points has been developing the drainage databases, some of the backflips that are necessary in order to get the grid-based model working. So that's been starting. We're using the information that we've developed for the Miseroute model. And from our early discussions, it was looking as if that information was mapping really nicely onto the information that was required for mesh in order to push that forward. The other pain points, these are less pronounced, is that there's some of the other tasks, as I understand from Ala and Dan Prince, and getting the vegetation data, getting the soils data, etc., aren't necessarily as automated as they could be. So looking at what Wouter's done and looking at the requirements for mesh and being able to combine that and push that forward is something that's going on. The other linkage is with next generation hydrological modelling. So as I mentioned, a lot of the work that Chris Marsh has been doing to set up CAtchment has got some overlap with what Wouter's been doing for his model agnostic model implementation, with his example with SUMMA. So we're in the early stages as to looking where some of those overlaps are and where some synergies could occur. There's some overlap with the forecasting theme. So a lot of the work that I showed with Louise Arnall, so she's really in the forecasting theme, and some of the work that she's doing that overlaps with the work that Chris Marsh has been doing to develop Snowcast. So that's fundamentally a workflow problem, or at least it is at the beginning, in order to get everything configured. So we're looking at it in this ways and looking at how the overlap between geospatial intelligence can be used to provide the underlying fabric that we need for the hydrological forecasting. So in terms of timeline, it's not in the future, of course, as you know, Prabeen, this is a lot of effort that's going on right now, and it's really exciting to see the progress. In terms of papers, Wouter's currently writing up his model agnostic workflow paper, and we plan to submit that to environmental modelling and software in the near future.
Another question I have, it's more curiosity, it's a bit philosophical. We are seeing so many studies focus on moral intercomparisons, are trying to find a silver bullet model for a particular reason, where you have a more approach of moral ecosystems or moral agnostic approach. Can you shed some lights on how we should be moving forward as a community and making best utilization of our resources?
So I've been quite rude in the past in my criticisms of model into comparison projects, and I've been rude in two different tracks, really. And some of these are beginning to be addressed. The first is that most model into comparison projects focus on the system scale response. So they're looking at the model simulations of streamflow or the model simulations of the carbon flux or something like that, and that's okay, but it doesn't really tell us much about the model behavior. I think we really need to go down into the processes, and we're seeing this in a lot of the work that Trish is leading, and other people, than the plumber experiments, etc., where they're saying, okay, looking at the system scale response, doesn't necessarily tell us much about the model behavior, so we need to focus much more on the internal processes in order to understand the differences among models and identify a clear path to model improvement. The other aspect is that model into comparison projects, by their nature, there's too many degrees of freedom. So there's so many differences between any of the participating models that it becomes really, really difficult to attribute the differences in the system scale response to the individual decisions that were made as part of model development. So as we're beginning to formalize this and think about, how to unify different modeling approaches across the community, we're getting into the realm where we can begin to do our own model into comparison project, where we've got a number of modeling options and the modeling frameworks that we're developing for next generation modeling, etc., next generation of CHM, that we can begin to do the model into comparison projects in a much more controlled way, where the differences aren't contaminated by differences in the numerical scheme or differences in the implementation of specific processes, etc. Those capabilities are still emerging and haven't necessarily been activated in the ways that are possible, but there's huge opportunities there.
Just to follow up on the same question, it's a question from Haley, and she's asking for us to move beyond, to more towards moral agnostic approach beyond GWF and into the broader Canadian modeling landscape. What do you think needs to be done?
Is that question as to how can the broader community begin to engage in the model agnostic effort?
Yes. So what do you think needs to be done for the broader community to move towards this moral agnostic approach?
It's going to be slow. So effectively what we're doing is to advance the science of modeling, where we're talking about best practices for the individual components of the modeling enterprise, and as it takes some self-reflection of the people who are involved in building these models to be able to say, okay, that's good, I can take that, or in some cases I can say, well, actually I think we've got a better approach for that, and then we're getting in the position where we begin to learn from each other. So through that self-reflection analysis as to how people are building their different models and disaggregating the problem into more tractable components, we can have a lot more synergy among the different modeling groups, and I think we're already beginning to see that happen. So again, I don't think that's something that we have to wait for the future. I think a lot of that's already underway.
We still have a couple of questions left to answer, but I'm looking at the time, so I'm trying to combine two questions into one. So the first question is there any plans to integrate large-scale model with cloud computing tools such as Google Engine? And also, how do you see the future of hydrological models, because of new data is coming on, so a lot of large data. So
the first question was on cloud computing. And the second question is, how do we use the new data that's available?
So how do you see the future of hydrological models in comparison to the data-driven model, considering that that now we are swarmed with various data sets?
Oh, okay. So I don't view mechanistic modeling and data-driven models as mutually exclusive. This question comes up, and I think every single seminar that I give is to what's the role of data-driven models. I think they're complementary. For data-driven models, there's many aspects of hydrology that are statistical in nature, and data-driven models, of course, have got a huge role to play there. From a mechanistic modeling perspective, I think we can learn a lot from data-driven models. So some things that we've been doing, look at the papers by Andrew Bennett, etc., in water resources research, looking at concepts of transfer entropy, using data-driven models to understand the flow of information through complex systems, and use that to evaluate how our models are representing that flow of information. Using data-driven models to provide an estimate of the predictability of the system, and evaluating the extent to which our models can match that level of predictability. Yeah, there's a lot to do there, and I think we need a lot of thought as to how we can use data-driven models in a way that helps improve our understanding of the processes. Data-driven models are never going to replace mechanistic models, because mechanistic models are really we really have a purpose of simulating surprise, extrapolating beyond the data, and we need to retain that. But yeah, there's going to be a lot of interesting things that we can do with data-driven models. With cloud computing, yeah, that's an option, and we've been looking at cloud computing in some of my previous projects that I've had with NASA. A lot of the work that we're doing at the moment is on high-performance computing systems. Where I see the benefit of cloud computing first and foremost is ways of sharing our model simulations with end users, so that we don't have to provide our end users access to supercomputing facilities, which in many cases is not possible, and that we don't have to install the models on end users' machines. So I expect a growth area in there moving forward as well.
I think we'll stop at there. We're already 2 minutes past 12. Thank you again, Martin. I also want to thank everyone that attended this webinar. Just a reminder that next month on 4th of February, we'll be having Professor Roy Brower from the University of Waterloo, who will be presenting an advanced in hydroeconomics. So please stay tuned. That will be all for today. Thank you again, everyone. Wish you a good day.